So we talk about electric potential. Electric potential energy. Electric potential energy is the energy stored in an electric field. So energy stored in an electric field. So okay, I know that. Okay, let's say we have two plates. This is a positive plate. This is a negative plate, and we know that the field moves from the positive. The field moves from the positive. Uh, Moves from the positive to the negative. So, and then whenever we have a positive charge, it experiences a force in this direction. But whenever we have but whenever sorry so, but whenever we have a negative, positive, then negative. But whenever we have a negative charge, and yet the field goes in this direction, this experiences a force in this direction. So this is a difference, one of the differences between gravitational potential and and electric potential. So let's have that in mind. So okay, this you read nothing much, and here, and you know that previously we have seen this equation when you're talking about electric forces, and this will be the equation for electric potential energy. So the difference now, okay, can we not speak about it now, but this is just a scalar. This is a scalar, this is a vector, this is a vector. So here, okay, maybe let me talk about this fact. So you remember here, we had the magnitude, so we're taking the magnitude of these charges r squared, because here we're talking of whenever we talk of the magnitude of a force, so we need to take the magnitude, because we know that the force is a vector. So at the end we will have a direction. So at the end, when we talk of a vector, so then at the end we'll have the direction of the force. So but in this case we talking about oops, in this case we are talking about a scalar, which is E, electric the electric potential energy, and here we just put the charges as they are. If charge 1 is negative, we put the negative. If charge 2 is positive, put the positive. That's the difference between the two. So here we want you just substitute the charges as they are given, negative or positive. Just substitute in. And here, okay, maybe if I can explain this. So you can see that when you have r to infinity, this is the same as dividing. This is the same as dividing by a very big number. So you know that when you divide by a big number, it reduces the overall value. So when you divide with a very big number, this means that this value becomes almost zero. So it means that UE goes to zero whenever r goes to infinity, because we are dividing with a big number. So let's continue. So now let's analyze this. So electric potential of a single charge is zero. So this is okay, potential energy of a single charge is zero. So in order to have a electric potential energy, you must have at least two charges, and you can find the energy between them. So this, you can see even from the equation, there's a requirement that you need to have two charges, and then you can find potential energy between those charges. This is what it says. So potential energy due to several point charges. Now when you have several point charges, so to find the potential energy due to more than 2 point charges, you add the potential energies of each pair. So okay, so here we have q1 and okay, all right, so here we have q1, here we have q2, and here we have q3. So what it says is that in order to find the potential energy of all this, so you need to sum this. What you need, like, you need to you need to make pairs. So the first pair will be this one, this will be, you'll pair this one, and you'll have a radius of r13, and then another pair you can also pair these two, so you will have r12, and also you can pair these two, so here you can have r32. So and then from there you can use this equation. So now you can use this equation, to calculate the potential energy for each pair. So we have, how many pairs do we have? We have 1, 2, 3. So hence this equation. So this is how you find the potential energy of of 3 points. So let's continue. Now, if you understand this, even if you have more than two, with more than three, you just need to add all the possible pairs, and then you will be good. So let's continue. Um, so potential energy due to several point charges. If a system contains only one charge, you remember, and this is how do we know that okay, how do we know that how do we calculate, or how do we find out that indeed the potential energy of a single charge is zero? this is an assumption you do, and you assume, okay, let's say I want to find this potential energy of this sphere. It has a charge of q, and then what I'll assume is that I'll assume a reference from infinity, which means that I'll assume a reference from infinity, very far away. I'll take that reference from infinity, which means that r is infinity. So r is in infinity. So that's why, so when you work out, when you divide, so when you divide, because this is the equation, so when you divide, so u is equal to k q 1 and the q in infinity. So say maybe in infinity we have q with a reference charge q at infinity. So then we will divide by r, and remember that r goes to infinity, which is very, very far away. So you're dividing by a very big number, so that's why u goes to 0. So that's why we say that for a single charge we have the potential electric energy as 0. So if the system has two charges, it is okay, you can write it like this. So then when it has 3, as we have seen from that diagram, you can have something like this. You just add the pairs. So when it has 4, you do the same thing. So this is as simple as that. So now let's go over this example. Example 17.1. 2-point charges. So 2-point charges. So a charge of okay, let me use a pen. So 2-point charges of -20 C, and then we have of 50 +50 separated by a distance of 8 kilometer. separated by a distance of 8 kilometers. Calculate the electric potential of the pair, okay, of the point charges, assuming that U equal to 0 when the two charges are infinitely far apart. So this is a very important definition. This definition, but there's nothing much into this definition than that it validates this equation. So the strategy is that electric potential energy of a pair of a point is given by this whenever we have this initial condition. So this would be an initial condition if I can talk in the language of maths. So here this would be the equation. So now if you want to work, so you know the equation. So you know the equation of potential, electric potential, which is Q1 Q2 over R, and we are given the charge, and remember when I say you put the charges as they are. So this was positive 50, so we have, and this was negative 50, so we have negative 50. So when you do that, or this is the K, the column constant, and then this. So when you do that, you'll find that when you do the substitution, you'll find that it's negative 1 times 10 to the power 9 joules. This would be the potential energy. Here it divided, they changed the kilometer into meters, because these are the SI units. So this would be the potential energy. So now let's go to this example. So calculate the electric potential for the array of charges shown in the figure. So we have okay, so we have array of charges. So we have 3 charges, and charge 1, we have this, and charge located at this, charge 2 located at this, and charge 3 located at this. So we need to calculate the electric potential, and we know the formula. This the formula of R. So we need to find the radiuses, the radii. Okay, so here we say, so we'll need to figure out the pairs. So this is how we figure out the pair. So we'll pair these two, we'll pair this one, we'll pair this one. So we expect 3 pairs. So let's go over that. So expect 3 pairs. So here we call this one R1, R12. So how can we find R12? So to find the distance, and you are given the points, so to consider. So here we have 0 0 0 0, which is here, and then we have what's a position at Q2. So position at Q2 will be, so it will be 3 4. So now remember that the formula for distance, because we want to find the distance, which is the R12. Formula for distance is so we say x2 minus x1 squared plus y2 minus y1 squared, all under the square root. So here we have, okay, so let's go over it. So when I do that, so when you take these points, when you take these points, so this will be this point and this point, and then when you put it into the distance formula, so let me just simply call it R1 now, R12. So we'll have R12 is equal to the square root, so it will be x2 minus x1, which is it will be 3 minus 0, which is 3, then squared, and plus, so here it will be y2 minus y1, which will be 4 minus 0, which is 4. So this will give us square root of 25, which is equal to 5 meters. So this is how they found this distance using the points. So we are good in this part. So now what will the next part? The next part will be to find this r12. So r12, so what do we have? So here okay, so we have q3 located at 3 meter. So we already know that it's 3 meter because we have 0 and 0. So it will be if we do that, it will be, so this is simply 3. So this give us 3 meter, and then this part now, so we want this part. So how will we find that part? So that part will say we need to subtract the points of q3 and q2. So in q3, the points we have what points we have in q3? We have 3 0, and in q4 q2, sorry, q2 we have q2, we have 3 and 4. So now when we want r23, we'll find the square root of, and then we'll say now this minus this squared, which is 0 squared, then plus this minus this, which will give us 4 squared. So now taking this, so it would give us 4. So we have that r23 is 4. So as you can see now, they've substituted the values. So here the combination q1 q2 of this radius, q1 q2 in this radius, so we have this formula, and then we go to 1 3, which is this part. So we have q1 pairing with q3, so we have this part. They've taken out the k. I think you notice that they've taken out the k. Actually the k is in there, they've just taken out the k because it's common. So and then go to this part where we're pairing a q2 and q3, so which is this part. So and then after substituting these values as they are, so this is, they did that, and then the final answer was this. So this is how you calculate the electric potential. I think it's very simple compared to the other exercises we had like in chapter 16. So now let's go over to electric potential. All right, so electric potential, just as electric field is defined as a force per unit charge, the electric potential V is defined as the electric potential energy per unit charge. So this is a statement in a formula. This is what it means. So this is how you calculate the electric potential. And the difference in this diagram, you will see the difference between potential energy and potential electric energy and electric potential, and this will show the importance of it. So you need to know this formula. So here, maybe let me try to explain these diagrams. So whenever you have a, let's say we have a plate, we have a positive plate to the side, and you have a negative plate this side. So you know that the electric field moves from the positive, so oops, So the electric, so we have a positive field and we have a negative, or plate actually, and then so you know that actually a field, the electric field moves from the positive to the negative. Now say that you have, so now so now say you have, a positive charge. So a positive charge will experience, in this field, will experience a force going this direction. And then if you analyze this further, you see that here uh, here this has higher potential. So this has higher potential energy. So it has a higher potential energy, and it goes to a of lower region of lower potential energy, just as in gravity. So hence that's why the movement is in this direction. But when you can see that here this is a region of higher potential. This is a region of higher potential, and this is a region of lower potential. Think potential as a voltage, and you will see that this is a region of high voltage, this is a region of low voltage. So think it like that. Think a potential as a voltage. Think it of in terms of a voltage. So here it will be a region of high, plus, that's why plus is called high and negative is called low, because plus is a region of higher potential and minus is a region of lower potential. And then so but in this diagram, so in the diagram, the next one, let me draw it again. So in this, here we have a positive, we have a positive, and we have a positive, right? I hope this will be clear. And then here, as you can see, the electric field still moves in this direction, because electric fields move from a region of positive to a region of negative. So you can say that it moves from a region of high potential to a region of low potential, because remember here, high potential, low potential. But now say we have a negative charge. So a negative charge, if the electric field goes in this direction, will go into this direction. I think you remember from the previous chapter. And say, what does this mean? This means that actually here, can use a different pen. So this means that here it has, in this region, at this point, it has higher potential energy. So it moves to a region of lower potential energy. So please understand these differences. So the reason this charge moves to the other side, or to this side, this direction, because it is from a region of high potential energy, and it moves to a region of lower potential energy, just as gravity. At a very high place, you have to have a higher potential energy. At a lower place, it has a lower potential energy. So but here it's a matter of the charge. Here, if you can think of it, here is, this side is saturated. Okay, this side is saturated of the negative, so this is a region of its higher potential energy, and yet here there's less saturation of negative charges. So that's why it moves from this side. So that's why it moves from this side to that side. So please note this difference. I hope I've explained this clearly. So electric potential is often shortened to potential. It is also informally called voltage. So you can see that now the units for potential is voltage. So the it's, you can call it voltage. So let's continue. So electric potential. Potentials do not have direction in space, they add. Okay, okay. What is important here? What is important here is to note is these formulas. What is important is these formulas. So the good thing is that the statement simplifies into formulas. So and then let's talk about potential difference. It's very important. So when a point charge moves from a point A to point B, it moves through a potential difference. Remember, we talked of high potential and low potential. So it means that between this, that means that in between, okay, this will be high potential, and then this region will be low potential. So when you talk of potential difference, this is what we were talking about, the difference. So and then uh, this is the formula, so it will be the final potential minus initial potential, and then the potential difference in change the potential difference is the change in electric potential per unit charge. So this is the change. That's what the statement is, that the potential difference is the the change in electric potential per unit charge. So when you rearrange, you have that the change in potential uh, electric energy is equal to Q times the change in the potential difference. So these are very important formulas. These are very important formulas. So now so we have talked of this. This is what I was explaining. This is exactly what I was explaining. So electric field and potential. So the electric field points in the direction of decreasing. So let's say electric potential. Okay, this is just to connect electric field and potential difference. So they say that as you can see, okay, here, remember that this is the region of high potential, this is the region of low potential. So remember when I say electric fields move from positive to negative, and this explains why. You see, uh, this is when you go to this direction is a direction of uh, decreasing potential. So they say the electric fields moves in the points in the direction of decreasing uh, potential. So this explains that. So now let's go over this example. Okay, let's go over this example. So a battery powered a battery. Okay, so a battery powered lantern is switched on for 5 minutes. During this time, electrons with total charge of this flow through the lamp, and 9.6 kilojoules of electric potential energy is converted, or we can say it's converted or lost to light and heat through, but not, I don't want to say lost because energy is never lost. It's converted, means that it is taken out or it's changing into another form. So we'll indicate using convention convection. You can use the negative. Through what potential difference do the electrons move? So remember, we need this equation that relates electric potential to the potential difference. So remember, this will be the formula. You can apply this equation to a single electron, but since all electrons move through the same potential difference, you can let Q be the total the total charge of the electrons, and so this will be the total charge of the electrons. You can calculate for each, but it will be convenient because they all move through the same potential, so it's convenient to just use the total, because this is the total of all the electrons. And then the change in potential energy be the total change in electric energy. So okay, this is what I was saying. The change in electric potential energy is negative since it is converted to other forms, so you need to put it in negative. So from this formula, as you can see, the formula that relates electric potential energy to electric potential. So this is the formula, because since we want the potential difference, so we would say potential difference is equal to change in potential energy over a charge. So this would be the formula, and then when you substitute here, they get positive 12 volts. So this is a 12-volt battery. So okay, now this is just derivation, and a potential due to a point charge. This is nothing beside, okay, what you can take here is that the superposition applies to potential as well. That as we have seen, we have added, like when you have many charges, you can add their potential. Or their contributions. So this is what we did. So we calculated. Remember, we calculated the distances between the pairs. So we used the pairs, something like that. All right. So and then let's go over an example. So here we have charge of this. Remember, mu is 10 to the power minus, I think, minus 6. It's located at this point, and then the charge Q is this amount, and then located at this that distance. So the charge 3, Q3, and so on and so on. So in A they say find the electric potential. So they want us to find electrical potential. Where is that point? At 0, 1. So here 0, 0. So they want us to find here at A. So they want us to find electric potential at A. So how do we do that? So here we're going to use, okay, remember the formula. You must note the formula. This would be the formula for potential. Now we're talking about potential, not electric potential energy. Now we're talking about electric potential. So this would be the formula for calculating electric potential. So when you have many point charges, so you know that, okay, when you say V is equal to the sum of K, Q, I, R, I. So say maybe we have 3 charges, so it will be 1, 2, and 3. So here you will have that the electric potential will be, so it will be the sum, which will be Q, K, Q1 over R1 plus K, Q2 over R2 plus K, Q3 over R3, something like that. So this is how we add. So here, and these things, so this would be the charges, or the point charges. Substitute, and that's all we do. So here in this example, then this is our point. So point A, so this will be our point. So now what we'll do is that to calculate our the distance, it will be this distance, and this would be this distance, and it would be this distance. So the distance due to q1 is called r1, distance due to q3 is called r3, and the distance due to q2 is called r2. So we just need to calculate those distances. So as you can see, if you talk about r1, so r1 it will be 3 minus 1, which is 2 centimeter. And then to calculate for r2, which is this part, so we'll need to subtract. Okay, this is how we do it. So in r2, so we have a point, okay, the point at a, which is 0 1, and then a point at q2, which is it should be 1 0. So now we use the distance formula. So say r2 is equal to square root, so we'd say 1 minus 0 squared, which is 1 squared, and plus 0 or minus 1 squared, which is 1 squared. So this would be r2 will be the square root of 2. So this is the answer, and r1 is this. So now if we go to, now we need to find this distance, which is r3. So r3, so r3 it will be, so we go to, okay, r3. So what points? We have a point at a, which is 0 1, and also have another point at q3, which is 2 2. So when you use the distance formula, you will have, so it will be 2 minus 0, which is 2, then they have 2 minus 1, which is 1. So here we'll have a square root of 5. So this is this answer. So now that we have worked out the distances between the point and the charges, so you can use the formula for, now that you can use the formula for electric potential. So where we have K, so we can say Q1 over R1 plus Q2 over R2 plus Q3 over R3, and then do the substitutions, and then we will have this is what they did this side, and they got this as the electric potential. So what, let's go to B. So in B, I say a point charge Q of this moves from a great distance. When I say a great distance, it means that when they say a great distance, they mean that R goes to infinity. And what is the charge in the electric potential? What is the change, or what is the change? What is the change in electric? What is the change? Okay. What is the change in electric potential energy? So now we need a formula that relates potential energy and electric potential. So okay, so now let's go over this. So you know this formula, so this will be the formula that relates, because we want to find electric potential energy. So changing, so here when they say, okay, I want to explain this, but this is very important. So if you write this, you will say that, because okay, so the final, so VA will be the final potential. Think of it like I said, say here it is our point A here, and then we're referencing from R equal infinity. So here you remember that the potential the potential energy is zero when r goes to infinity. When r goes to infinity, remember I said this is simply as dividing by a very big number, so this makes this very small, closer to zero. This makes u 0, so the try here, they have 0 here as the initial potential. So when we do that now, so I think I've tried to explain this part. So when you say u e is equal to q, say v final and minus v initial. So remember, so v final will be a, and then here is 0 because you are referencing from infinity. Remember where r is infinity, so this why this is 0. So now when you do the substitution, and when where we have this charge and you have this potential, so you can work out the electric potential. So you see that we're given the charge, and we had work. Okay, we are given the charge, which is negative 5.0 nano. Nano means the n means 10 to the power minus 9. So, and then we have worked, because we were interested in point A, so we're interested in point A. We have worked the potential difference. Oh yeah, we have worked the potential at A. Yes, we have worked the potential, not the potential difference, but we have worked the potential at A, and then you can find the potential difference from the reference point of where r is infinity. So this way we calculated the potential difference, and then from there we're able to substitute. I hope you get this. So we have worked this part. We have worked VA, remember the potential at A. So we were given, this is Q, and then we have worked the potential at A. Hence now we can have potential, the electric potential is this. So now let's go over quickly over this. Okay, so here example 17.5, 4 equal positive point charges Q are fixed at corners of the side as A is the electric field 0 at the center. Okay, they say they're positive. That's okay. These are positive charges. Okay, they are positive, equal positive, and then this we have a center here. So we have a center here, and then here, remember the fields move from positive, so it moves out from the positive source. So this means that experiences, so we have this side and this due to this one, and also we have force going this direction due to this one, and then also we have force due to this one going this direction, and we have force going this direction due to this one. Remember, we've worked electric fields this way. So here clearly we can see that now that E is 0 here. The electric field is 0 at the center, and then P is the potential 0. So we can, for that we can then calculate that, because the way you find potential, okay, is the center. You calculate potential at the center. Remember how we calculate potential. We use this formula. Okay, let me go to this side. Okay, this is what I was saying, and I hope you'll read around it, but I think here it's obvious that the electric field is zero. So now let's talk about the potential. So what is the formula for potential? Okay, this is the formula. Okay, let's write this together. So we want to find the potential at the center, at the center. Oops. So how do we do that? So since we know we're given this part, so we need to calculate these r's, these r's. So this distance, how do we find this distance? Let's calculate each r. So here from here to here, so I can use, okay, here if I take, okay, let me do this. If I take half of this, and then I know that these sides are equal. And what does that means? If I know if this is 90, okay, actually this is 90 as well, this is 90. So here this is a 45 angle and this is a 45 angle. So so I know this angle half. Okay, maybe I don't want to confuse. Let me explain it this way. Yeah, if I draw a line here and if I draw a line here, you know that this is 90, and then I've cut the 90 in half, and this, what does that mean? This means that this angle, the half angle, is 45 degrees. Copy, agree. So now if I want to find this distance, how do I do it? So I know I'm given so okay, here remember it's 90 degrees, so I'm given the hypotenuse, which is s, and here this is 90, and then I know that this angle is 45, so I know this angle is 45 degrees. So but I want this side, so what would I do? So I have the adjacent, so I go to SOHCAHTOA. So I have the adjacent and I have the hypotenuse. So you know that cosine 45 is equal to, so what is the adjacent? I'll call it r, so r, and then what is the hypotenuse? Hypotenuse is s. So what is cos 45? So what is cosine of 45? So cosine supposed to be half. So cosine of 45 is 1 over square root of 2. So this will be is equal to r over s. So now when you make r the subject of the formula, you'll get this part. So you get this part. So now that we have derived we derive that derive the R for all this part. So how many R's do we have? So we have, okay, maybe instead of calculating the R's like that, let me just write the formula. Remember that the formula for potential is given by if you involve many charges, so it will be the sum of k qi over ri. So I'll have q, okay, because they're all the same, so all the charges are the same, so it will be q, but r1 plus q r2 plus q r3 plus q r4. And what is r? So r, so v, so actually the r's are the same, so this is more like adding four things, adding same things like this. And then we know that r is equal to s over square root of 2. So when we substitute that, and we have we'll have 2 times 4k q over s. So this will be the potential. This will be the electric potential at that point, at the center actually. So now let's go over this last example.